for today is relativity. And relativity is the dependence of some physical phenomena on relative motion of two observers, meaning that two observers might be observing the same events. On observing the same events, they will give different inference because the observation is different due to their inertial frame. What do I mean by inertial frame? If a body, relativity has to do with, from the idea of relative motion. A motion is in which one body is stationary and the other one moves. So if an observer is in relative motion, one is in motion with constant velocity while the other is stationary, and they are trying to observe the same event, they will observe different things and will give different inference. You understand? So there are two relativity theories. We have the special relativity theory and we have the general relativity theory. So we are going to start with the special relativity theory. So this special relativity theory deals with some physical phenomena, or you call them events, except gravity, some other physical phenomena except gravity. And there is a postulate given by Albert Einstein based on this special relativity theory. There are two postulates. The first one says that the law of physics are the same in all inertial frame, whether you are in stationary point or you are in motion with constant velocity. The law of physics is the same. The law of physics, when you are observing a certain law of physics in your different inertial frame, the laws will be the same. While the second postulate states that the speed of light in the vacuum is constant and the same in all inertial frame, regardless of whether the observer is in motion or the source producing the light is in motion. So these are the two postulates that abide the special relativity theory. This special relativity theory has consequences. It has consequences. Let's look at in explanation of those postulates. When we say the law of physics is the same, it has been generalized compared to that of the mostly experiments. It has been generalized by Newton that in optics, heat, or whatever, the laws of physics observed in different inertial frame, that means in different position, whether in stationary or in constant motion, is always the same. And the same thing implies if the second one, if the speed of light changes in different inertial frame, that means that the first postulate is wrong. But since the speed of light in different inertial frame are the same, then the first postulate is what is accepted and correct. So now, the consequences of special relativity are the relativity of simultaneity, of simultaneity. Then we have time dilation. Then we have contraction of length. All these are physical phenomena that depend on the relative motion of two observers. Contraction of length. So let's start with what? Relativity of simultaneity. When you are talking about simultaneity, we are looking at events, physical phenomena that occur and observed by two persons or two bodies. An observer might see it to take place at the same time, while the other see it to take place one after the other, due to their difference in inertial frame or positions. So, and that is definitely going to be a relative motion. Let's take a look at a bus. Talking about simultaneity. If I have a bus here moving with constant velocity, or v, towards the right direction, and there is an observer who stood outside, a stationary observer, while we have another observer, O prime, that sits at the center of the bus, moving along the line with the bus. And there is a thunderbolt that strikes the bus at the front, point B, and also here point A. The observer O, that is stationary, will observe that the event take place simultaneously, that the boat strikes the bus at the same time, because by the time he is going to observe that, the bus will have moved forward and the two impulses will reach him at the same time. Let's take a look at the diagram here. The bus is now here. This point is where the observer in the bus is, while this is the stationary. Then the impulse from the two strike will reach the observer O at the same time. Then he is going to observe and say the events take place at the same time, simultaneously. But observer O prime will give an inference that the thunderbolt strikes the bus at the front, then at the back, because he is in relative motion with the car, with the observer O. So this is one of the explanations or principle of relativity applied in simultaneity. Let's look at time dilation. In time dilation, let us assume an observer, two observers. They are trying to observe two different events in their different inertial frame. One is stationary and the other is in motion. That is what relativity is all about. One is stationary, the other in motion. By the time they are going to give the interval of time for the two events to take place, the interval of time will be different from each other because of their inertial frame, their position, their present position. Let's take a look at a bus as well, moving with constant velocity v towards the right. Then an observer in the bus, a mirror is placed on the roof or on the ceiling of the bus. Then observer on a flashlight. Observer O prime, while there is another stationary observer standing here. So observer O prime on a flashlight to the mirror and measures the time it takes to reach the mirror, and the light travels distance d vertically, d. Then the observer measures the time it takes to reach the mirror. Then after the reflection, the observer also records the time it takes to reflect. So it shows that what the change in t, this p represents proper, because that is the proper view according to the observer inside the bus. So it's going to be what? Distance over time, distance over speed, since speed equals distance over time. So time will be what? Distance over speed. So two distances are covered now. 2d. The first one for the propagation of light towards the mirror, and the second one for the reflection, all over c. C is the speed of light, because we are considering that speed of light in different inertial frame is the same. So this is one observation of the O prime. This is what the O prime will observe. But the observer O, will give a different inference, because ordinarily we know the height of the mirror towards the roof is d, according to this observer. But this observer O will give an inference that if the light is to reach the mirror, then we have to propagate, the light have to be propagated at a certain angle, because he believes is what his observation will tell him, or we show him that by the time the light will have reached the mirror will have moved forward, because this vehicle is moving with constant velocity. So as the vehicle moves, the mirror also moves. He will observe that the light has to chase after the mirror, but it has to do that in a certain angle from his own position. He is considering his own position and not this observer's position. So then he believes the light has to be propagated in this small angle, so it will be able to reach the mirror. Then we are going to look at the distance traveled by him, which is now more than 2d. According to his own observation, because he has increased the distance of the mirror already. Now, so the distance is going to be what? The changing time multiplied by the speed, c, the speed of light, change the average distance. we are considering the average distance, that's over 2. Then the same thing is going to observe the distance of the mirror as it moves forward. So, and since the mirror moves with the velocity equal to that of the bus, then we are going to have v change in t all over 2 as average distance of the what? Of the mirror as well. So using Pythagoras theorem, we can get a relation here that says c change in t over 2 all squared is equals to v change in t over 2 all squared plus d squared from Pythagoras theorem. So evaluating the squares, we have c squared change in t squared over 4 minus is equals to v squared change in t squared all over 4 plus d squared. So that will give me c squared change in t squared all over 4 minus v squared change in t squared over 4, which is equals to d squared. So factorizing and removing the change in c squared over 4, we are going to have c squared minus b squared all equals d squared. So from there we have change in t squared into bracket c squared minus b squared equals 4d squared. So change in t squared, we are making the time, we are making it a surrogate formula since we are looking at time dilation. So, and this is the time observed by this O. Why this is the time observed by O prime? We are going to look at the relationship between the two. So we are going to have 4d squared all over c squared minus b squared. So finding the square root of both sides, I have changed in t squared. T now equals to square root of 4 is 2. Square root of b squared is 3. Then we have square root of c squared minus b squared. Factorizing this, I have changed in t. We now have equals to 2d all over c into bracket 1 minus b squared all over c squared after factorization. Then I discover a relationship that change in tp, which is the what? The interval of time that was observed by the O, the observer O prime. Now a relationship already exists between the what? Observer O prime, the time observed by the O prime and time observed by O, who is stationary, and this in motion. So then we can give that as, since 2d over c is equals to change in tp, then change in t will be equals to change in t, that's proper, all over the roots 1 minus b squared over c squared. So this can also be rewritten as gamma multiplied by change in Tp, where this is equals to 1 all over square root of 1 minus b squared over c squared. And this is called the Lorentz factor. So this is where we are going to stop this topic for today. We continue from there in the next video. Thanks for watching our YouTube video. Please subscribe to our YouTube channel. It's free, and click on the bell beside it to notify you when we drop a new video.